Okay, I think we'll get started. So, fun day today. We're going to learn about symmetry and these things called point groups. And our job will be to be able to look at a molecule and assign it to a so-called point group. Now, this is a topic that is traditionally taught in a physical chemistry course. But I think we can do some of it. We won't do the full understanding of everything, but we'll really focus in on just looking for symmetries in molecules. And I think this is just a wonderful way to help develop your three-dimensional thinking. Because as we know, chemistry happens in 3 dimensions. And the better we are at thinking about molecules and picturing molecules as 3-dimensional objects, the more intuition we're able to get about some kind of chemical system that we're interested in. So today we're going to talk a little bit about the types of symmetries, what a symmetry is, and then the main job today will be learning how to use a systematic approach to assign molecules to point groups. So let's start with the symmetry here. There's several basic types of symmetry that we look for. The first is rotational symmetry. So if I have a water molecule here, certainly if I do a full rotation, then the molecule is back to where it starts. And that's what we're looking for with a symmetry. So you can imagine if you were to close your eyes, and then either I don't rotate this or I do rotate this. When you open your eyes again, this will be in exactly the same position in space that it was. So certainly every object, if we go all the way around, will be back to where it started. But many objects have additional rotational symmetry or higher rotational symmetry. And so let's imagine this water. If I rotate this about this axis that's coming straight towards you, or when I turn it like this, going straight up to the ceiling, I only have to rotate it half of a turn. So this has a rotational symmetry that's greater than one full rotation. So we call that a C-type symmetry. The operator for that is a C operator, and the subscript on this is N. And you can think of N as two ways. You could think of N as 1 over the fraction of a turn. So here I do a half a turn, so 1 over 2. If I flip that, then I have 2. And so this has C2 rotational axes right here. Now, if we could also think of it as I can stop 2 times. I don't have to stop, but I can stop 2 times in a full rotation. So you can think of N that way. So one of the things you do when you look at a molecule is you want to identify the axis that has highest rotational symmetry. And that will be called the principal axes. Now sometimes there's a tie, and then it doesn't matter which one you choose as long as it's the highest value of N. So here's an example of C2. I'll grab ammonia here. Now this is an example. If I point the principal axis at you, if I start like this, I go 1/3 of a turn. So this would have a C3 symmetry. And my axis again here is like this. And when you're looking for axes, point your finger and then try to find the axes of highest symmetry. Right? So this has a C, this would have a C3 symmetry. All right, the next thing we look for are mirror symmetries. And there's 2 basic types, vertical mirrors and horizontal mirrors. And these are relative, not to the room, vertical, horizontal, but they're relative to the primary or principal axes that you found when you were looking for your rotational symmetry. So for water, for example, if I hold my water this way, my principal axis is like this. But if I hold it like this, pointing it at you, then my principal axis is that way. Vertical always means contains the axes. And now when we're looking for planes, use your hand. So use your finger. If you're looking for axes, use your hand if you're looking for a plane. So a vertical plane will always contain that principal axes. So if we look at water, we can see a vertical plane here, right? Because if I reflect across this plane, then this hydrogen will go to this hydrogen will go to this hydrogen, and oxygen will stay in place. But I also have a mirror this way, because all these atoms lie in a plane. And so this is an additional mirror. Now you'll notice here a sigma V and a sigma D. We're not going to make a big distinction here. This is called vertical, this is called dihedral. And I'll just I might mention it again later when we're going through the systematic approach. But it doesn't much matter to us at this level in terms of just trying to understand or just trying to develop our 3D thinking and identifying symmetries. Let me grab that ammonia again just to as a second comparison. So here's ammonia, and we've discovered that the principal axis is like this, and so we said that's a C3. So that defines our up and down, no matter how I hold it. And so now we're going to look for vertical mirrors, and yes, there's one right here that involves the plane that contains these two and the full principal axes. And then there's this one and this one. So this has 3 vertical mirror planes. Now, horizontal mirror then means if our principal axis, wherever we put our principal axis, however that's pointing, then the mirror is perpendicular to that. And so if I have this kind of at some weird angle here, then my mirror is like this. If I hold it like this, it's like this. So if I look at ammonia, I don't see a horizontal mirror because these guys would get reflected upward. Likewise with water. So water is a molecule that also does not have horizontal mirror symmetry. All right, inversion. Inversion, kind of pinch your fingers like this, use a point. That is inverting through the center of mass of the molecule, and or center of symmetry, I guess. So you would have this hydrogen would go up this way, this hydrogen would go up this way, and this oxygen would come down just a little bit. And so it would end up looking like this. Now, notice I had to rotate this. It's not a rotation. It's think of this coming up and through and out the other side, up and through and out the other side. And ultimately, it would end up looking like this. And so this does not have inversion. Ammonia again, up and out the other side, up and out the other side. So if I'm holding it like this, once inversion is done, and again, it's not a rotation, but it would end up like this. So we started down and towards you with this one, and these were backing away off side to side. When they invert up through, then we would be like this. And of course, this is different than how we were holding it this way. So this does not have inversion. Let's look at this with this. This is just a cube. So a perfect cube will have inversion because each corner of the cube can invert through the middle and out to the other side. So this would be an example of something that does have inversion. And now finally, there's this combination move that is a rotation followed by a horizontal mirror, and that's called improper rotation, and that's given the symbol SN. So the N plays the same role as the N for the regular rotation, and then we follow that with a horizontal mirror. Now, that's a difficult one. That's probably a more difficult one to see. So I just concocted this shape here that has an example of S4 symmetry. So notice that this alternates up and down, up and down. So if I find an axis of primary symmetry, it has to be a C2 because I have to have, see, the ones that are both up are towards you and directly away from you. The ones that are both down are side to side. So the highest rotational symmetry is C2. So there's C2 symmetry. But this has S4 symmetry because if I make a fourth of a turn now, and then here's my axes that I'm turning on, if I make a horizontal mirror, then that will reflect these guys down and these guys up. And we're back to where we started. So this has an S4. So that's an example of an S4. I'll illustrate it one more time. So we make not a half turn, but a fourth of a turn. So that's like that. And then we reflect here in this mirror. So like this, like this, and like this. So both of these are up now. So this is a more difficult one to see, but it's an important distinct symmetry that molecules have. Notice that, let's do ammonia here. Let's see if this has an S3 or an S whatever. So we could try an S3, that would look like that, right? But then we have that horizontal mirror, which would end up looking like this. We could try an S6, which would be going like this, and again, we would end up like this once we horizontally reflect it. So this does not have improper rotation. All right, so these are the symmetry elements. We're gonna the collection of symmetry elements for a given molecule form what's called a group, and we're not going to talk about the structure of these so-called algebraic groups until later in the curriculum. But once you have a molecule, it will have a particular set of symmetries. Then that particular set of symmetries is what's called a point group. And there's just a limited number of so-called crystallographic point groups, 32 of them, and molecules fall into those crystallographical point groups. There's a few extra they fall into, but basically there's a limited number of groups, and they're all completely solved. And not only have they been solved, but they've been thoroughly investigated. And we've come up with streamlined ways of assigning molecules to their correct point group. Now, if two molecules share the same point group, they could be quite different molecules, but they'll have certain things in common. And these things that they have in common can be really helpful in understanding chemical bonding, which we'll be talking about much later in the curriculum beyond these introductory courses, and their vibrational behavior and rotational behavior that's important to vibrational and rotational spectroscopy, which again, we'll wait until we get more thoroughly into this. But as I mentioned, by doing this, by practicing assigning molecules to point groups, it's just a wonderful way to develop your 3D thinking. Then you can take it even a little bit further and just think of molecules in their condensed formula, try to draw the Lewis structure, then try to draw the wedge dash structure, and then try to assign them to a point group. So it's really good for challenging yourself all the way back to the Lewis structure, because that will determine ultimately the geometry, which then ultimately determines the point group. Okay, so we'll practice a little bit more, and I'll show you this systematic way. So I'm going to go to the computer now, and unfortunately, it'd be great if I could be there and you could have your access to a whole bunch of molecules, because it just takes a lot of practice. But if you happen to have a model kit, you could build these. It's nice to hold these things in your hands. Or even if you have other kind of constructor set type things like Legos or Tinker Toys, you can build some stuff and try to assign them to point groups. It doesn't have to be a molecule. Any kind of geometric shape can be assigned to a point group. And then, but without that, if you don't have that, there's a really wonderful website for practicing. Now, it's not something you hold in your hand, but you can use your mouse to rotate molecules in 3D space, so it's pretty good for that initial learning. And like I say, once you ultimately want to wean yourself off of having to hold anything in your hand and just be able to see the molecule in 3 dimensions without having to touch it. All right, so let's do that. I'm going to switch here now to screen mode and start with this flowchart. So this is that systematic way of assigning molecules to a point group. So we start at start, and then very simple question. And I've noticed students overthink this sometimes. This is just, is the molecule linear? That is, do all the atoms fall on a straight line? So oxygen, O2, or carbon dioxide would be linear molecules. Water, of course, is bent, so that would not be linear. So very simple question here. And that, if yes, it pulls you over into these linear groups. And let me say a little bit about this. If you think of a linear molecule, you can, the axis of highest rotational symmetry, let's maybe see if I can zoom in on this. Maybe, yeah. The axis of highest symmetry is infinity, and we can see C infinity here, because you can just barely turn the molecule and just infinitely turn the molecule and it stays the same as it was before. And so if we have this linear molecule, then the horizontal mirror would be cutting that perpendicularly. And so something like carbon dioxide, which has linear with carbon in the middle and two oxygens, would end up in, we would answer yes to that, and that would end up in the D infinity H group. Carbon monoxide, just carbon and oxygen, would end up in the C infinity V group because there wouldn't be a horizontal mirror. So once we decide it's not linear, then we find the principal axes like we talked about earlier. So water, it was a C2. Ammonia, it was a C3. That crazy contraption was a C infinity. Or sorry, that was a C2. Okay, now there might be cases where there is no highest symmetry. So C1 is the highest, and so there's no, we'd say there's no rotational symmetry, or the rotational symmetry is a C1. That's kind of the same thing. So then we head off over here to these really low symmetry groups, and then we just look for whether there's a mirror there, or inversion, or nothing at all. And so there's three possible groups there, and by asking those questions, we can assign them to the correct one. Now, is there more than one C3 axis? Now, what this is saying here, and again, this is a point where I find students get stuck a little bit. Let's say you find a C3 axis as your highest symmetry. If you don't, if you find a C2, then you just blow right through this question. But if you find a C3, then you need to look for another C3 axis. And also remember that if you find an axis, say, and you orient it pointing straight up, the one you can't, if you put your finger pointing straight down, that's the same axis, so that's not a different axis. So this is looking for a different axis that is at least C3. If that is true, then you end up over here, which are the high symmetry groups. And they're easy to distinguish. If there's a C5 symmetry, then it's an icosahedral or an IH group. If there's inversion, which we showed the cube had inversion, cube is an example of an OH group. And then if there's no inversion, then we have a tetrahedral group or a TD group. An example of this would be carbon, like carbon tetrachloride. Now, here's the question I think the students have the most trouble with, because this is a little cryptic here. So once we decide on the principal axes, so let's say it's a C2, then everywhere else in the flow chart, when we see N, then N is 2. If like for ammonia, we had N equals 3, then everywhere else in the chart, N is 3. So once you establish your principal axes up here, then for the remainder of the chart, that value is what you use. So let's look here now. Are there n perpendicular, and this is what's confusing. It just had to, I didn't have enough space in this box here, so I always have to explain this a little bit. So if you've got your principal axes and you orient it, anyway, but let's orient it straight up. What we're doing is we're looking for C2 axes that are in the plane that is perpendicular. So I've got my C whatever axes up here. I'm looking for C2s, just C2s, and are they in this plane? So that shrinks your view really nicely to a single plane. Can you stick your finger in the single plane like this? And then if you can rotate the molecule and it's back to where it is, then that's a C2 axis. And you look for as many as you need to satisfy the n value. Now, if you find one, then you'll find that the others are there. So that's something that is a little trick. Sometimes they're hard to find, all of them. And so know that if you find a few of them, the others will be there, and sometimes they're a little harder to see. The axes that are most hard to find are when they don't go through any atom. They just go through empty space, which is totally fine, but they're harder to recognize. Now, if we answer no to that, we end up over here in the C groups. These are of sort of mid-level symmetry, more symmetry than the totally non-symmetric C1, CS, and CI, and much less symmetry than the high symmetry groups. If we answer yes to this, we end up in the D-type groups, and these are of higher symmetry because they have those extra perpendicular C2 axes. Notice here, let's go this way. This is the one that students have a little trouble with too. That's that S axis. Now, we only have to look for an S2n. So if you've got a C2, then you look for an S4. If you've got a C6, you look for an S12. And this also has to be, so is the principal axis also an S4? So you only have to look along the principal axis. You're not going to be looking somewhere else in the molecule. And so these, once you know that and can lock in on that, that makes this a little easier to find. Then we answer yes, and we can end up in the S-type group. These are fairly rare. There's not too many molecules that have this example, but they certainly can. Notice here that this looks a little weird. This flowchart kicks us back over here, which means that you must have gotten this question wrong. And that happens a lot, actually. So this can be a little savior to get us back to the D groups. Now, if you end up through this route, then you should always go back to this question, find those axes, and make sure you end up down here again, and shouldn't get shot off over to these groups. Okay, so that's the flowchart, and now it's a matter of practicing the flowchart. So I'm going to go back to the room view, or the whiteboard view, and let's work through the flowchart together on a few molecules. And then I'm going to go to that website, and we'll be able to see how you can use that for extra practice. All right, let's just do this. Okay, so we look at this. Is this linear? Yes. So it has a C infinity axis right here. And then there's white up here, red over here. So I look for a horizontal. I say no. So this ends up being a C infinity V. Okay. Let's try water itself. So here's water. Is it linear? No, it's bent. Where's my principal axis? Right here. It's a C2. So all through the rest of the chart, n is 2. I go down and ask myself, do I have more than one C3? Well, I don't have any C3s, so I can blow right through that question. Then, do I have two, right, because n is 2, perpendicular C2s. And again, that doesn't mean perpendicular to each other. It means perpendicular to the principal axes here. And so I come in like this, in this plane, right? And I can see right away that no matter where I have my finger in this plane, a rotation is going to bring the hydrogens up. So I answer no to that. And I head off to the right side of the chart if you're looking at it. So off to the C charts. Now it says, is there an S4? So I have a C2. Here's my principal axis, my C2. So an S4 would have to be rotating a fourth of a turn. So I'll do that here too. So that will rotate now. So they're coming at you. And then a horizontal plane, or horizontal mirror, so that would flip up like this. Now notice, students make a lot of mistakes here too. In order to, we can't really do the mirror with our hands here without breaking the bonds. So this hydrogen would come up. Notice when you do this, you're doing a rotation. That's not really a mirror. So this hydrogen comes back over here. So be careful when you're doing these horizontal mirrors that you're really thinking about the mirror, the reflection, when you do something like this. Okay, so this would be no, so it has no S4. So then that takes us down into the C groups. Is there a horizontal mirror is the next question. Well, no, that will put these guys up. And then are there two vertical mirror planes? Well, there's one right here, as we found earlier, and there's one right here. So yes, so this would be a C2V group. Let's do ammonia. So I'll do this a little bit faster. So ammonia C3. It's not linear. So, and then principal axis C3. So I have a C3, so I have to be careful. Do I have any other C3s? Well, notice any rotation now that isn't this one is going to move these hydrogens. So no. So now we head down to the important question about the perpendicular C2s. So I go here, right? My perpendicular C2s are going to be in this plane. So no matter what, the hydrogens would end up here. So we'd answer no to that. We look for an S6. So that would be a sixth of a rotation. And then mirror reflection. And that's going to put the hydrogens again on the other side. So no S6. Now we look for a horizontal mirror. Well, that would pop those hydrogens up. So no. And then we look for vertical mirrors. Well, there's one here, and one here. So this is a C3. This is a C3V. Now, sorry, here I've got smaller molecules here. So let's look at this one. So I look at this one and I can see a C3 axis. Right? So it's not linear. I have a C3. So I have to look, do I have other C3s? Well, I can't. If this is one, this is not another one coming straight down from the top. So I've got C3 here, no other C3s. So now I'm looking for perpendicular C2s, and now I do have those, right? I have that. So that's in the plane of this. My principal axis is straight up, so I'm coming in here straight at you, and I have there's one. Now this set of hydrogens isn't any more special than this one, so I have 2, and then I have 3. So there's my 3 perpendicular C2 axes. So that takes me off onto the D side. And then I ask, is there a horizontal mirror? Well, there is in this case, because use my hand here for a mirror that will reflect all the hydrogens into each other. And so this ends up being a D3H. Let's look at this one. So this one, not too symmetric, but it looks like there might be because there's these 2 greens and these 2 purples. So I can rotate those into each other. It's not linear. So I have a C2. I don't need to worry about the C3 or higher. And so I now look for perpendicular C2s, and I can try that, but I can't. There's no. So again, this is the principal axes. One thing to try is to try to line these guys up, but when we do that, we don't get the same. The carbons flip back and forth on that, so we don't get the same there, and so we have no perpendicular C2s. So we head off towards the C group. Now we ask ourselves, is there an S4? Well, that's going to, a fourth of a turn is going to put these carbons like this. So there's no way that's going to happen even after the mirror. So we answer no. Now, is there a horizontal mirror? Well, there is, because all these lie in the same plane. All these lie in the same plane. So there is a horizontal mirror. And so this will be a C2H point group. Let's do this cube. So highest symmetry axis is a C4. There's a lot of them, so we answer yes. Is there a C5? No, we said the highest was a C4. Is there inversion? Yes, the corners of the cube can go into each other, and so there is inversion. And so this is a OH group. Let's make just a slight change to that. Let's just take one of the corners and make it a different atom. Now all of a sudden, we've lost a lot of symmetry. So a little trick of the trade is if there's only one here, that's got to lie, and if there's going to be a symmetry axis, that's got to lie on the axis, because if it doesn't, it's going to move. And so we can immediately key in, just like this. I'll try to hold it so that this corner is obstructing the back corner like that. And hopefully you can see that there is a C3 rotation. There's a C3 rotation. And so it's C3. There's not going to be any other C3s because that would move this single one. We look for some perpendicular C2s. Well, that's gonna move this, right? So there's no perpendicular C2s. We look for an S. We look for a S6, right? So that'll be a sixth of a turn, which looks like it might work. But then when we do the horizontal mirror, the silver is going to be pushed below, and the yellow will come up. So we don't have that. And so now we're looking for horizontal mirror, no, because that's going to move the silver. Vertical mirrors, yes. So this ends up being a C3V. So we go from a high OH group down to a low C3V group just by replacing one of those corners. Okay, well, that is what we've done here. Isn't enough practice for you. What you want to do is practice more and more. So really try to learn that flowchart. And in my experience, it's taken somewhere between an hour of good hard work to 3 hours of good hard work for a student. And 99% of the students, if you really put that effort in, learn how to do this. And there's not too many things you can do in your studies that over the period of just an hour or 3 hours of practice really changes how you view the world, because you're able to see these symmetries now more clearly in 3 dimensions. All right, let's just finish here with, I'll go back to the screen, or the computer screen, and we'll look at that website. So here we are at this website, and this is really well done. So let's go to, well, there's a tutorial, and this talks about those operations that we've talked about, and it goes through each of these types of reflections or these symmetry operations, so you can get a little practice with that. and has some examples. So there's that. Let me get back here. Where I think you can get a lot of practice is the gallery, because what this has done is this will let you choose. Now the danger here is you're going to know the answer before you start, but you can choose one of these groups. So let's say you want to learn about it. You want some examples of a DN group. So let's do like a D3. And then that will pop up on the screen. And you can rotate it with your mouse. Not quite like holding it in your hand, but gives you a chance to get a little bit of a 3D help. And of course, this is free and quick, so a good chance to do that. You can look for an SN. So let's look for something that has an S6 here. Pretty complicated molecules that they have to break the right amount of symmetry, but still have enough symmetry in order to have a S, like an S6 in this case. So these can become pretty complicated. So we've seen now that you can practice all these different ones. So then it'll go back and give you a little bit of a challenge here, and you can just grab one, and it won't tell you what it is. Now, these guys have their own spreadsheet or flowchart. It's different than the one that I'm working with here, and that you can get from the link in the description. But it so you can either use that. I mean, certainly there's many different types of flowcharts, and so you can either use the one we're using, or you can use a different one. And the bottom line is to be able to get these correctly assigned. And so there's tons of practice here, and you just work through. So does it have, right? And then you say no, and then is there a unique C3? No, and you can just keep working through the flowchart that way. So it's not perfectly aligned with our flowchart, but can still give you a lot of practice here. And you might not even want to do that. You just, I think somehow, or you just work your answers through whether, I think if they're right or wrong, you can get to the final answer and then check yourself. Actually, maybe, oh no. Yeah, so just a good chance to get some practice. So if you work through all of these, I think you'll really be able to take any molecule and assign it to a point group. Now the next step is to not be looking at anything like this, and simply look at the chemical formula, put it into a Lewis structure in your head, put it into a wedge dash diagram in your head, pick it up in your head and turn it around and figure out the point group. When you can get there, then you've really developed your way of thinking about chemistry. All right, so that's it for the tutorial. And again, practice. The flowchart is linked to in the description, so you can grab that.